Hello community, isn't it a beautiful day for DSPy 4? And I know what you're gonna say. You say, hey, you already have 3 videos, come on, we know everything about it. And you are absolutely right, and therefore I answer now your question. Hey, I don't have the money for the huge LLM implementation or model development. Is there a topic where I can contribute to AI? And I mean research. And I think I have an answer for you. Let me show you. Now, you know the basic multi-hop DSPy program looks like this. Very easy. We have here initialization, and then we have a forward pass where we have here the query generated. We retrieve some information, and we are able to answer a very complex query suddenly. So, just to make sure that we're on the same page, let's say I have a complex question, CQ. How do solar panels contribute to environmental sustainability? Now, the idea of a multi-hop program is simple. We take this complex question and we divide it in simple question 1, 2, and 3. This is now here our complex question. Now, you know that for the simple question 1, we go to our any rack system and we go for the retrieval. And we retrieve a simple answer for the simple question 1, simple answer 2 for the simple question 2, and a simple answer 3 for the simple question 3. So this gives us the chance, and please note, I don't care about the retrieval module. You can go to Google and do a keyword search. You can go to an encoder transformer and just go S-squared cosine similarity, or you go to a SQL database, whatever you do. It's not important what is your retriever. Just important, you have complex question divided in simple question, and the simple question can be answered by a rack system. Beautiful. This particular question you can divide here, GPT-4 did this for me, into first, what are the basic functions of solar panels? To answer how do solar panels contribute to something, you have to understand, hey, what are the basic functions? The second question is, now looking to the target environmental sustainability is, GPT-4 generates a question, how do solar panels reduce carbon emissions? This is just a very tiny fraction of this topic. And the last one, to link it now from the beginning to the end, is, what are environmental benefits of using solar energy? So you see, this is just one of many possible 3-step combination that GPT could give me for this complex question. And you see, it is always here. Solar panels you find always, and the environmental you find always there. So, beautiful. If we have these blocks, you know what we're going to do now? Yes. We think that those are simply nodes in a graph. So we have a simple question 1, we hop to simple question 2, we hop to simple question 3, and we get an answer. The simplest graph you can imagine. We have edges. Edges can have different strength, can have different weight tensors in different dimension for our graph. So why not use this knowledge? Just to show you where we are now on the textual side. The complex question is the same. How do solar panels contribute to environmental sustainability? GPT-4 generated for me 3 simple questions, SQ1, SQ2, SQ3. And then any retriever that you have, Colbert version 2, or you go with any Google, whatever, retrieve relevant passages for each of the simple queries. So the passage retrieved by the retriever model for a hop 1 question, hop 1 query is, solar panels convert sunlight into electricity. Another retrieved document was, hey, they are composed of photovoltaic cells to generate power, and so on. You do this for hop 2 and hop 3. And then, next step is, you accumulate all the context that has been retrieved from some external data, external to our primary, for example, large language model. And then GPT-4 combines this to generate here the final output, the final answer in a paragraph. You say, okay, so wait a minute. If I see this now here as a graph structure, I can say, okay, why only have one answer generated here for my simple query? What if I go with 3 different receivers and I go, for example, here with R1 to a vector embedding similarity. With R2, I go to a SQL database or NoSQL or whatever you have. And R3, hey, why not do a simple keyword search? You see, now you can enlarge here your answer space significantly. But you also see you cannot only do this on the first node, but you can do this on all nodes. So you have now additional bootstrapped information. Now, let's look at this in detail. If we now say this graph is just one of many possible graph or subgraph structures, because maybe if I use here now 2 different bridging questions, the simple question 4 and the simple question 5, I do not need here to go over the simple question 2. Now, using this alternative, you see this simply becomes a graph optimization problem. So what we do, we just try it out. No, not we. An AI system, GPT-4 or whatever you choose, will try this out, and then we just measure the performance of each specific subgraph pathway. And subscribers of this channel might say, hey, wait a minute. This sounds like an optimization problem we have already solved. Because they say, hey, the first video was about DSP, then we went to DSPy for the PyTorch programming, where we have here our bootstrapping and I have here our compiler functionality for some self-automation, self-optimization for the perfect pipeline structure. And you say, hey, what about now we go here? We know PyG, the torch geometric data program. And as a subscriber, you have seen this here where I use PyG on an SBIRD system, so more or less on a vector store. And you say, hey, can we not go there and combine this? So you see, this is to answer your question from the very beginning of this video. There are so many options you can think of. And this methodology has not even been explored here by Stanford University, because they focused here on this. And you see, within 5 minutes, we together came up with a further optimization idea, that we use a model we know, if you have seen this video, and we just integrate this. And you can do this as, I don't know, if you start here with AI at the university, or if you want to have a nice PhD, you have so many options. You don't need here this huge infrastructure. Just use your brain. So, yeah, the process is now as follows. We have now a new graph structure. And what do? We now transfer this graph structure in our textual input for a large language model, because we are operating with LLMs. So what we have, our simple question 1 in blue, and then we have 1, 2, 3 simple question answers that have been retrieved from different sources, from external databases, you know what. And we have SQ, S4, S5, SQ3. So 1, 2, 3, 4. And this is now the amount of additional retrieved data we have to augment now our RAG system, retrieve, augment now here our data set and our inference logic. Beautiful. Now, you remember the step 3 was just accumulate all the text that we get, deduplicate, whatever is duplicate or triplicate, just delete it. You just need it once, and then GPT-4 or whatever system you have generates the final output. And you might say, have we to do this for each prompt? No. Remember React. And I showed you here in video 2, I think, the React main human prompt template from 1000 runs of trial and error. And they have here examples. Question, action, question, 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 question. So 1, 2, 3, 4, 5, 6 examples. And this is exactly what the amount that we need. We need 3 to 5 examples. React is even more complicated. We just go here for a multi-hop question without any action. So let's say we go with 3 examples. So what we need is here an this exactly here in pink or whatever this is. This is what we need for our self-automated template structure here to have here the perfect, if you want, template for the task. So we evaluate then if we have this final output, the specific output, now our prompt structure on our, I don't know, ChatGPT or whatever model you have, GPT-4, to find the best performant prompt. And you know this in, as I showed you, in DSPy, you use here the teleprompter, you compile here your RAG system, you have a specific training data set, and the system finds a self-optimized prompt structure for us. No human prompt generation of any template anymore. And this looks interesting. But you know what is now here the benefit of this? This is now for my knowledge domain. Now for my specific output that I can focus now on a specific topic like general astrophysics, or I want to be real specific. I want to go with only astrobiology answers. So you can tune your system to the exact behavior that you want from your DSPy RAG implementation. Plus, you can also go here for the data format that you want here exactly. And this is nice because remember, in the React, this was here for some general examples because this React had to work for everything from, I don't know, poetry to US news to US politics to science to cooking recipes. But now we can choose here particular, maybe only theoretical physics. So we are here much more focused on the domain knowledge, and this is really beautiful. So the task is easy. The task here is find the optimal subgraph, and we have a tool for this. We have PyG, torch geometric data, and I showed you here already how to implement this with a vector store. So you have the code available. You see, this has not been published yet by Stanford, so we are the first to explore this. You see this, I think, hopefully, first time here. But you know what? There's another benefit. Think about this. Now, this is a bonus since you are still here, and I think I'm already 10 minutes into this video. But think about it, what we can do now. If we have this graph structure, and let's say this is a complex graph structure here, and we have, let's call it an alpha domain. This is our dominant graph. But you know from graph theory, the mathematical theory behind this, we also have not connected graph structure in our complete graph. Let's call it a beta sheet. But this beta sheet has also been constructed from semantic information. Let's say this is here astrobiology. And this is here general astrophysics. But unfortunately, let's just assume for a minute, in our data set, there was no connection between those two. So now we have the idea that suddenly we have another mathematical space to operate in. And if we use now DSPyG as a methodology, you know what? We have 2 options we can use here to find here new solution, to bootstrap new solution. Isn't this beautiful? Because either, as I have a video here on graph machine learning, we say, hey, you know what? If I apply my methodology, my code that I have here on this graph structure, I can find out, no, the system, the graph machine learning comes back and says, you know what? This node here and this node here, those 2 red nodes, I found, based on the semantic information in the training data set and the training you give me and the context you give me, that those nodes belong to the same topological cluster or to the same thematic cluster. And you say, amazing. So now you are able to say, if those 2 red dots in the same cluster, you can bring them closer together in the graph space. Or, of course, if you're a subscriber of this channel, You have another option, edge prediction. Here, look at the edges. If we have a complete graph, we can do some edge prediction calculation. Based on the semantic information here of the complete data, this program will give you here a probability. And maybe we find out that this particular green node here and this particular green node here, connecting the alpha domain to our beta sheet, the probability that there could be a real edge connectivity is very high. Maybe this is the top 1 edge prediction. So if you would think about how to connect the two graphs, for example, just as an idea for you to experiment further on, you can say, I run an edge prediction and I look here at my top candidates, my top 3 candidates, where I can try here to find a bridge functionality based on the semantic topic of my data set. And this is beautiful. So you see, DSPy combined now with PyG, you find solutions that have not been published. You can make your PhD on this topic or whatever. You have now, and this is another bonus I'm excited about, access to the complete knowledge domain. Now, I know this is a simplification, but stay with me for a second. Let's say here we have here the frame of the complete knowledge domain. All of this is astrophysics. And now we have connected on our dataset and what our GPT-4 has been pre-trained and fine-tuned on, or your LLM has been pre-trained and fine-tuned on. We find here this graph structure. But we find an unconnected subgraph, a beta sheet here. If I apply now the tools that I have from graph machine learning, from graph neural network applications, I can connect now here also, let's call this region of my graph space. You know, this is just a topological space. This space has no vector, has no metric, has no distance at all. But I can now explore here the unexplored space here of my alpha domain graph structure, and I find filaments outside of our alpha domain that might be helpful, that might carry important information. So I can explore, let's call it a complete knowledge domain in this graph structure. And you might say, but hey, wait, we have here the vector embedding. The vector embedding does this for us. Really? Are you sure? Let's have a look at this. Now let's say here we have a vector space. So we have a distance defined, we have a metric defined, and beautiful. And now here we have here our simple query, and then we retrieve with any retrieval you want from your RAG module 3 partial answers specific to this query. And you just imagine in the simplification, then we have 3 data points with important information outside of this structure of the vector embedding. Now what we do, if we do now here, if you are in a vector store, if you do a vector embedding cosine similarity function, you have your query. So you find the vector embedding of your query and you have your query vector. And then either you go here for a local environment or you go here for the angle or whatever metric you choose. You look here for, let's say, a local environment, what is close to your query vector. And you find here, hey, this green dot here, this is a similar vector, and this green dot is also a similar vector. So the vector store, the vector embedding representation comes back to you and tells you, hey, I found 2 additional data points, 1 and 2. And with this retriever will only integrate these 2 data points. And you see what we do not achieve. We do not achieve with vector embedding to discover those other vector points that might have important semantic data information for us. Because here we had graph machine learning, a complete different learning methodology, a different representation of our problem, of our semantic data connectivity. And this allowed us to find maybe highly predictive edges. Let's say, yeah. So you see, there's another beautiful idea if you combine existing elements and you create something new and you find, hey, this looks really interesting, and maybe I do this next weekend myself. But just to show you, if you understand the methodology, it is really easy to combine it. Combine multiple elements, think about what is the pro, what is the con. Does this bring new insight into the topic? And if yes, go for it. And yes, you know me, I have also been answering here another of your question. And one of the questions was, hey, a chain of thought and a retrieval augmented generation program, what does it mean that they can self-bootstrap in DSPy to increase here the language model to retrieval model pipeline performance? Now, since I've chosen this particular example from the beginning of this video, now I also answered here this question. Isn't this beautiful? Another question answered. Yes. Now you might say, was there something else? No, because nobody asked me, hey, for compiling, when I said, hey, we use a teacher program consisting of an ensemble of 2 Multihop Llama 2 LLMs, nobody had any question about this. This is from the original paper, from the original literature of DSPy. And I think this is a beautiful idea of kind of a parallelization if you use here an ensemble of multi-hop LLMs here. But since nobody asked, hey, I'm not gonna answer this. However, if you made it to the absolute end of this video, you got a bonus too. And here you see now the code for the multi-hop question and answer form for DSPy. If you want also include citation of your original document sources. It is in DSPy really beautiful to implement. This is from the original implementation. So you just generate a cited paragraph in the field, and those fields include here the original source, the original citation. So you see here 3 class definition, and you have here a long form question and answer DSPy capability that just not gives you an answer here with a multi-hop question and answer system. So you answer a very complex question, you divide it in simple question, you find the simple answer, you combine all the simple answer, you then find here the optimum, plus you have here with this cited paragraph, you know exactly where each sentence in the answer is coming from. From what original document is this coming from? And this is the code implementation for multi-hop question and answer with citation. And this is it. This is now the final end of this video. And it would be great to see you in my next one.